Okay, section 3.4 is titled Zeros of Polynomial Functions. And if you're thinking to yourself, Miss Quigley, we've been finding the zeros of polynomial functions because those are where the graph crosses the x-axis, you would be correct. The problem is, as we get to higher and higher degree of polynomials, the algebra skills that we have used so far are inadequate to be able to solve and find the zeros of polynomial functions. So we need a few more tools in our toolkit to be able to solve and find the zeros of higher degree polynomials. One of the theorems that we can use to find potential zeros for a higher order degree polynomial is called the rational zero theorem, or the rational root theorem, sometimes it's called. And it basically says if a polynomial is written in standard form, that's what all of that is, and has integer coefficients, then p divided by q is a potential rational zero of f. Now what I mean by that is, if you take the very last term, the constant, that's going to give you the p-value, because any number that multiplies to make that last number, the constant, can go in the numerator. And then the a sub n, which is my leading coefficient, if we take all the factors of my leading coefficient and put them in the denominator, then we can write a list of all of the potential rational zeros of the function. Now, potential rational zeros means all integer, like 1, 3, 5, 7, all fraction, like 1/2, 3/7, and the negative versions of those as well. This is not finding any of the radical, which are irrational numbers, or any imaginary numbers, but any rational real zeros we're going to be able to find using this theorem. So what we're going to do to find a potential zeros or possible zeros list is we're going to take a set of numbers that includes the positive and negative versions of factors of the constant term, that's the last term, divided by factors of the leading coefficient. Okay, this feels like a lot of work, and it is, because we're going to have to do some trial and error eventually to find out the actual zeros of a polynomial, but it has to come from this list of potential rational zeros. So let's just see how we use this. We're going to list out all of the possible rational zeros of these two equations. So what we're going to do here is we're going to highlight the last term, the constant, and we're going to highlight the leading coefficient here. The last term for this particular problem, that's going to be p, that's 4. What are all of the numbers that multiply to make the number 4? Let's start at the beginning. 1 times 4, and then, so we have 3 unique numbers in this list, 1, 4, and 2. The q value is -1. Now I know that it's negative, but I'm going to ignore it because we have a plus or minus in our formula here, so it's fine. But what are all the numbers that multiply to make 1? 1 and 1. So only one unique number, which is nice. When we're making our list of potential rational zeros, what we're going to do is we're going to make a combination of every number on the top, p, divided by every number on the bottom, factors of q. Meaning, and this one is easy because the only q value I should use is 1, I will have in my list plus or minus 1 over 1, plus or minus 4 over 1, and plus or minus 2 over 1. How did I get this? Great question. I'm so glad you immediately asked. What are the 3 unique numbers on the top? 1, 4, and 2. So see how I have them here, 1, 4, and 2. How many unique numbers in the list for q are there? 1. So that's why there's only one type of denominator. Now this is actually 6 numbers because we have the positive version and the negative version of all of these numbers. So if I were going to simplify this, because like the fractions, 1 over 1, we know that's 1, we would say that this list has -1 and positive 1, -4 and positive 4, -2 and positive 2. Because that's all of the versions, the 6 things from my formula, plus or minus p's over q's. Do we see this? Now this gets complicated when the number that is p or the number that is q has a lot of factors. So for example, if we look at the second one, The p, remember, is the last number, which in this case is -2. I politely ignore the negative because we don't technically need it since we have plus or minus in our formula. And then my q value is 15. If p is -2, what are all the things that multiply to make 2?
1 and 2.
1 times 2. Nice. That list is not very long. That's good. What are all the things that multiply to make 15?
1 and 15.
Uh-huh.
3 and 5.
How many unique numbers do I have on that list?
4.
4. So there's going to be a lot of combinations of these numbers when I have 2 unique numbers for p and 4 unique numbers for q. You put all of the p's over all of the q's. So our list of potential rational zeros here would be positive -1 over 1, positive -2 over 1, positive -1 over 15, positive -2 over 15. I'm going to pause. I'm halfway through this list, and I just want to make sure we're all on the same page. Do we see how each of the unique denominators, 1 and 15, each had the unique numerators, 1 and 2? So I have the denominator being 1 with both numerators. I have the denominator 15 with both numerators. So following this pattern, what would be the next number I put in this list? 3 over
1.
Wow, no, Miss Quigley, I'm doing this wrong. 1 over 3, sorry, you were right. And then 2 over, keep the denominator.
1.
And then 1 over 5. And what's the last one? 2 over 5.
Jeez, I'm lost. Wait, 2 over 1.
Give it a second. Give it a second. If we were writing this all the way out, using your nice, neat handwriting, this would be -1, positive 1, -2, positive 2, -1/15, positive 1/15, -2/15, positive 2/15. You see what I'm doing here?
There's so many commas.
Correct. There is a lot of commas here. But we want the positive and negative version of each of these integers
So it's 32 of them?
and fractional numbers. I don't know why I put the plus sign. We get it. We don't need that. So that all 16 options appear on this list. Now, why are we making this list at all? Valid question, because that's a lot of work if we're just making a list of potential rational zeros. What we've done is we've given ourselves a list of numbers that we could potentially divide this polynomial by and get a nice remainder 0, meaning it divides evenly.
There's 16 of them?
Hopefully not all 16 of them. Hopefully you choose one towards the beginning that actually does divide that polynomial. Y'all ready to see one from start to finish?
Not really.
We're going to do it anyway. So if we're using the rational zero theorem to solve a polynomial, basically we're going to turn to this theorem when it can't factor, when it can't be done factored by grouping, when there's no GCF, and we're kind of out of options at that point. This one we turn to the rational zero theorem. So using the zero theorem, you're going to list off the potential rational zeros like we did up above. So remember, that is always going to be p's over q's. Then we're going to use synthetic division. Synthetic division, much nicer than long. To test these potential rational zeros to find one that divides the polynomial perfectly. Because that means we have found an actual zero for the function if it divides evenly, remainder 0. Then whatever is left over, hopefully we'd be able to factor it with like an X puzzle, guess and check, or grouping, something easier, so that we can finish solving the question. Let's hop right into it. For this problem down here, and I'm going to stop highlighting the p's and q's because it's just too much. What is the p-value for example 3's polynomial? -6. What are all the numbers that multiply to make 6?
1 and 6.
And
2 and 3.
Okay, what is the Q for this polynomial? 1. It's so nice when it's 1, because what are the only numbers that multiply to make 1? 1 and 1. Now we can take a couple shortcuts here with our list of potential rational zeros, because they'd all be divisible by 1, yes? So really, instead of writing it as all of these potential rational zeros over 1, let's just use our math brains for a second. We're going to call this plus or minus 1, plus or minus 6, plus or minus 2, plus or minus 3. We have 8 options here, and none of them are fractions, which is nice. One of those 8 options, or a few of those 8 options, should perfectly divide into this polynomial. So that's what we're going to start testing. It's a trial and error situation. I always like to try positive numbers first. So what I'm going to divide by is I'm going to divide the polynomial by 1. I'm going to use synthetic division to do this. So I set up synthetic division using any of the numbers off the list. I go from start to finish, going from positive to negative. That's just my habit. Do we see why I set this up? Where did I get those numbers from? From the equation. My polynomial is 1x cubed plus 2x squared minus 5x minus 6. So we bring down, we multiply, we add, we multiply, we add, we multiply, we add. Do we follow? Synthetic division. Since my remainder, the last number, is negative 8, does this 0 factor the polynomial? No. Wrong. We don't like that. Sad face. Okay, moving on. That one didn't work. It was a potential. It didn't work. Sad face. We try another one. Let's go negative 1. We just go down the list. So we're going to retry synthetic division. Hopefully this one works, because if it works, then we can move on. But if it doesn't, we would go down the list of all 8 potential rational zeros. We bring down, we multiply, we add, we multiply, we add, we multiply, we add. What do we get at the end this time? That's good. We want that. That's a happy face. Because if we get a 0, that means that that particular 0 creates a factor that perfectly divides this polynomial. So what we're going to do is we're going to grab this. And we're going to grab this. And we're going to write the polynomial that is left after we divide these two things. Now, we did this last class with medium results, but this would be x plus 1, and then x squared plus 1x minus 6. This was my dividend. This was my quotient. Do we see how I got all of these things? So here, we're going to take a short pause, and if this trinomial, this polynomial here that's left over, is factorable, then we don't have to continue using the list of potential rational zeros. You're just going to try to solve it. AKA, we're going to factor. What are the numbers that would multiply to negative 6 and add to positive 1? What are things that multiply to negative 6?
2 and 3.
Can I make 1 out of the numbers 2 and 3?
Negative 2 and 3.
Negative 2 and positive 3, yes? If those are the zeros completely those are the factors completely factored out, then the zeros of this function would be negative 1, 2, and negative 3. Those 3 numbers were all on the list of potential rational zeros when we started. Negative 1 was there, 2 was there, and negative 3. Is that what you're raising your hand for? Thank you. Yes, negative 3 is there. So yeah.
If we did like 2 on the synthetic division, we would have got 0 too.
Correct. Yeah, if you had happened to choose 2 as your first testing point, it would have come out with a remainder of 0, and then would have factored to find the other 2. And same thing with negative 3. If you had divided by negative 3 first, it would have come out with a remainder of 0.
So there's like multiple.
There's multiple ways you can do it, yes. Can we try another one? All right, example 4. It's going to have us find all the zeros of this polynomial. Now, my brain first is like, 4 terms. Can we do grouping? And I look, there's not a GCF for the second term. So we can't use grouping, which means we would have been able to skip the rational root theorem. Instead, we're going to use the rational root theorem to solve this. To do rational root, we need P's and Q's. What is P?
3.
-3, but we treat it like 3 because our formulas have positive and negative in it. The factors that make 3 are 1 times 3. Ooh, that's a nice short list. We like that. We're going to go for Q. What is Q?
1.
Nice, which is 1 times 1. That's a nice short list, which is great. That means that the list of potential rational zeros that I can have is plus or minus 1 and plus or minus 3. Numbers on top divided by numbers on bottom, but the numbers on bottom are just 1, so we can just write it as the integers plus minus 1 plus minus 3. Okay, again, I like to just go in order because it makes sense to me, do things in an orderly fashion. So we're going to divide by 1. This would be 1, 7, 11, and -3. This is synthetic division. We bring down, we multiply, we add, we multiply, we add. What is that, 19? Yep. We multiply, we add. Uh-oh. Did that one work? No, sad face. So what do we do? We go to the next one. Sad face. Okay, what's the next one? -1. Nice. We'll just go down our list. So we're going to divide this time by -1. 1, 7, 11, -3. We bring down, we multiply, we add. We multiply, we add. We multiply, we add. Did that one work?
No.
Rip. All right. So sad face again. What should we try now?
The next number.
What is the next number?
The next one.
3.
The next one, 3. So we go back to the list of potential rational zeros. We did +1, -1. Neither of them worked. We'll try +3. Fingers crossed. Here we go. 1, 7, 11, -3. Okay. Bring down, multiply, add, multiply, add. Yeah, what's happening here? It's getting real big all of a sudden. Sad face. Just all of a sudden got real big. So we're really hopeful that -3 works. Here's 1, here's 7, here's 11, here's -3. We bring down, multiply, add, multiply, add, multiply, add. Hooray! Because we got a remainder 0. This is an actual 0 for this polynomial. So what now?
That's your answer.
If only. We're wanting to find all of the zeros. So far we've only found 1.
I'll get it back.
We do. So what we're going to do is we're going to take this back to, tape this back together is the sentence I just said out loud. You're going to take this divisor and the quotient, put them back together and start to factor. So what this would look like for us is that we would have x plus 3 and x squared plus 4x minus 1. Yes, we see where I'm getting this from. I couldn't show both at the same time because it's all the way over here. 1, 4, -1. 1, 4, -1. Okay. So we start to keep solving. We're going to factor this. We're looking for numbers that multiply to 1 and add to 4. Uh-oh. What are the numbers that multiply to 1? 1 and 1, right? Is there any way I can make 4 out of 1 and 1?
No.
Yikes. This is not factorable, which means we need to dig back into chapter 1 skills. When something was not factorable and it was a quadratic, What formula did we use to solve it?
Is it the U thing?
Not the use, that's when it's degree 4.
Oh, we do the quadratic formula?
We do the quadratic formula, which means if we were solving this from here, we know the first 0 would be at -3, check done, because we know we solved that one already. To find the other one, we would do x equal to -b plus or minus the square root of b squared minus 4 times a times c all over 2a. X equal -b plus or minus the square root of b squared minus 4ac all over 2a. From here to the end, it is literally just reducing this quadratic formula. Do as much as you can each step. So this is going to be -4 plus or minus 16 plus 4 over 2. What's 16 plus 4?
18, 20.
20. So we're going to have -4
I think it's 16.
plus or minus the square root of 20 over 2. We have to break down 20 if possible. Is 20 divisible by a perfect square?
Yes.
Which one?
Wait, no, 4.
4. 4 is a perfect square. What is 4 the perfect square of?
2.
2. So this can actually factor down to 2 square root 5 over 2. If you need to make the tree and watch that 20 become 2 root 5, that's fine. That's what I'm doing in our head.
I'm already good.
Yeah, we're almost done. Because isn't 4 and 2 are both divisible by 2, yeah?
Yes.
Which means this actually becomes -2 plus or minus the square root of 5. There's our second 2 zeros. The reason this number is not on the list, unlike the first problem we did, is because these are not rational zeros. They are called irrational zeros because they have a square root in it. They have a radical. They're called irrational. So they don't come from my list because my list only shows me pretty numbers, fractions, and integers. So at this point, once you get to the point where you can't factor anymore, it's not factorable, use the quadratic formula. You will either end up with a rational number or maybe an imaginary number, complex number, something like that. Questions, comments, concerns? How am I going to say this? The rational root theorem is a little bit of an outdated method because we have a lot more access to graphing software and graphing tools than old mathematicians did when the rational root theorem was absolutely necessary. So the fundamental theorem of algebra is going to allow us to fast forward through a little bit of the rational root theorem because we're going to be able to use a graph to find some zeros. So what I mean by that is, let me back up. The fundamental theorem of algebra basically means that the degree of the polynomial is the number of zeros you should find. They might be repeated, they might be complex, which means imaginary, but there should be the number of zeros equal to the degree of the polynomial. But if you don't see a real zero on an x-axis, then there has to be imaginary roots that finish this up. The other thing we remember is that imaginary roots always come in pairs. They're called conjugate pairs. We did this in a previous chapter. A plus bi and a minus bi go together. If you find one, you have to know the other one exists, which is also why the quadratic formula has the plus minus in it, to get us both the positive and negative imaginary numbers. So here's what I want for you to do. On your calculator or Desmos, whichever one is easiest for you to pull up, I want you to graph this function first because we're going to find all of the zeros of this function. And if we didn't have graphing tools to fast forward, we would be doing the rational root theorem. We'd be making a list of p's and q's to give us numbers to test. But if you have a graph and you can see what this looks like, you're going to be able to take a shortcut. A mathematical shortcut using what we know about graphs, roots, and x-intercepts. So I'll give you 1 second. I want you to graph it on your calculator or Desmos, however you work best. Since we're looking at this graph now, what do you notice about the graph of this polynomial? Maybe particularly pay attention to like the x-axis. Where does it cross and or touch the x-axis?
The extra.
Yeah.
Wait. Give me a minute.
We should be looking at it. Where does it cross or touch the x-axis?
None? Wait.
It
What am I looking at?
it touches at the number 2, yes?
Yes.
Wait.
How do you zoom in on your?
So here's what we know. From the graph, we learned the following things. So from the graph, we see that x equal to 2 must be a place where a 0 exists because the graph touches and turns at the x-axis there. Oh, but it touches and turns around.
What did you just write?
From the graph.
I don't know, miss. It looks like hieroglyphics.
You're right. Let me write it with better handwriting. Y'all learn to read cursive.
Yeah. Yeah, that wasn't cursive.
That's in cursive. Is that better?
That was
That's a
dark
little bit
skin.
From the graph, we see that x equal to 2 is a 0. Particularly, it's a 0 where the graph touches and turns around. What does that mean for us?
It's a touch and go.
Right?
It's afraid of
It bounces. What's the multiplicity? 2. That means that we are going to be able to divide the polynomial by 2 twice because the multiplicity is 2.
So if it was like 3, you would do it 3 times.
If the multiplicity was 3, we would divide it 3 times. So what we're going to be able to do now is instead of having to make the list of potential rational zeros, we're going to take a shortcut. We know this one works because we have a graph of it. So we're going to take this polynomial and divide it by 2 twice. This is going to be 1, 0, -6, -8, 24. What? Why the 0? What is? Because, yeah, we're missing the cubed term. Nice. So we bring this down, and then we multiply, add all the way across. Multiply, add, multiply, add, multiply, add, multiply, add. Hooray. But we said this touches and turns. So I'm not just going to do this once. How many times did I say I was going to divide this? Let's use our paper to the best of our abilities. Let's just go ahead and do it again.
Wait, how we do it? Oh, oh.
Bring down, multiply, add, multiply, add, multiply, add. Amazing. Now, did you see any other zeros on that graph?
No.
No, there was no other places where this is going to touch and turn and or cross the x-axis, which means our other 2 zeros are going to be imaginary. This would be one where I wouldn't even attempt to factor this quotient. I know it's not going to factor because it's not showing up on the screen. If it showed up on the screen, but it was like, oh, maybe it's like a half, you need to factor. But what we're going to do is we're going to take this quotient, the second quotient, and we're going to use the quadratic formula for it. Meaning I would have x minus 2 squared multiplied by x squared plus 4x plus 6 equal to 0. And I'm not even going to attempt to factor that quadratic because we know it's not going to work. There's no numbers that multiply to 6 and add to 4. My first 0 is at x equal to 2 with multiplicity 2. My other 0 is going to come from x equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. Memorize my formulas. So we start to reduce as much as possible. So this is negative 4 plus or minus the square root of 16. Yep, minus 24 over 2. What is 16 minus 24? Oof. We're overwhelmed. What's 16 minus 24? 8, but let's make it negative. So negative 8 over 2. We got a negative underneath a square root. imaginary, which we knew this from looking at the graph. There was only 2 places where it touched and turned. Well, 1 place where it touched and turned. The other one has to be imaginary. We'd also break down the number 8. Is 8 divisible by a perfect square?
Yes.
4, correct?
Yes.
And 4 is the perfect square of 2. So this is going to be -4 plus or minus 2i square root 2 over 2. Again, if you need to put the tree out there for 8, you can put the tree out there for 8. Now 2 divides all of these things, so I can reduce this to -2 plus or minus I radical 2. Those are my other 2 zeros for this polynomial. I have positive imaginary number and negative imaginary number. Makes sense, they come in pairs. So again, since we have the ability to graph the rational root theorem, while I still want you to practice being able to do it because I'm going to ask you to, it becomes a little bit old-fashioned since we have an ability to see on a graph our real/rational zeros. And if we can tell what it is, like the number 3 or in this case 2, we can divide by that one instead of having to go through the list and do trial and error like we did up at the top. It's a fast-forward step. Make sense? So when you're doing synthetic division, what are you looking for it to be perfect? 0. That's a huge thing right there. If you can get a remainder to be 0, you know you have a 0 of the polynomial and you can continue dividing. That's a great question. Why did I do this twice? So from the graph, because this touches and turns, like the graph like touches 2 and turns around, I know it's a multiplicity of 2 because touch and turn, which means that 0 occurs twice. So I divided by the 0 twice. If it had just crossed through the x-axis there, I would have only done it once. Yes?
Wait, so if it was like 4, we would do it 4 times?
There would be no way for us to tell that it's 4, but yes, theoretically.
Okay.
Other questions? That was a good one. I have a bonus question for you. Let's say we were graphing something. Don't write this down, just listen. Let's say we were graphing something and on our x-axis, the polynomial did this. So it crosses at like, let's say this is 3 and this is 5. What numbers would you divide by? 3 and 5. Not 2 and 2, 3 and 5, because those are the places it crosses. We just chose to divide by 2 twice because ours touched and turned at 2. Yes? Yes.
Where did you get the x equals 2 for the graph? Oh wait, no, never mind. I got it. We graphed it.
Yes, that's where we got it from. Thank you. You got it. You answered your own question.
I answered my question. I said it out loud.
So we've done one direction where we've taken a standard form polynomial and we found the zeros. But what if we start the other direction? The linear factorization theorem is going to start you off with the zeros and ask you to work backwards and write the polynomial.
Miss Quigley, what is that? What is all those letters?
Yeah.
I see.
So it says, and this is a mathematical like theorem, right? It says if we have, this is a standard form polynomial, okay? If the standard form polynomial has particular zeros, then those zeros can be multiplied together to create the polynomial, so long as we have a starting term. In words, an nth degree polynomial can be expressed as the product of a non-zero constant, a number in front, and a particular number of linear factors where each linear factor has a leading coefficient of 1. We're going to start with the zeros, end with standard form. You ready? You'll notice that this page is entirely blank. We're going to take the whole page. I'm showing you this so you don't use big handwriting. Don't use tiny handwriting. Don't use big handwriting. All right, we're going to find a 4th degree polynomial with real coefficients that has -2, 2, and I as zeros, such that f of 3 is equal to -50. Here's what we know so far. We know that this polynomial f of x can be made by some beginning term a sub n and then the factors created from these zeros. Okay? If those are the zeros, then the factors that represent them are x plus 2, x minus 2, x minus I, and x plus I. Remember how every time we got this in factored form, we just took the opposite sign? Do it again. We have the opposite sign. We just make the factors. Now, wait a second. It only told me I. Why did I get two things here with I's? Plus and minus. Conjugate pairs. So imaginary roots or zeros always come in pairs. Fabulous. Okay, that's our start. Good job. We've started. The next thing we're going to do is we're going to work to figure out what a sub n should be, what that leading coefficient should be. So what we do is we use the fact that f of 3 is equal to negative 150 and we solve. So we're going to put equals negative 150 a sub n, but then every x I should fill in a number. What number should I fill in for x based on f of 3 equal to negative 150? 3. So everywhere there was an x, I'm going to put a 3. There are no x's left. The only missing value, the only variable we have left is a sub n. One variable, one equation, we can solve. Let's start. This would be 5. This would be 1. Whoa, and now I need to multiply 3 minus I and 3 plus I. But hopefully, you remember back to chapter 1, this is the difference of two squares. So instead of having to double distribute here, we can take the shortcut that it's 9 minus I squared. So we square, because these are opposites, we square the first number, we square the second number, subtract them. It is the difference of two squares. Are your spidey senses going off at all? What is I squared? It's negative 1, so we flip the sign. So really, this step should say, let me write this down. It should say negative 150 equal to a sub n times 5 plus 1 times 10. 10?
Yeah, 1 plus 9.
1 plus 9. Because the negative 1 becomes, change the sign, 9 plus 1, so 10. 5 times 1 times 10 is what? 50. So then we have negative 150 equal to 50 a sub n. How do you solve for a? That's why I asked it. What number is in front of a that we need to go away? So what do I do to solve? No. Divide by 50. It is currently multiplied by a sub n, so we divide by 50. Negative 150 divided by 50 is negative 3. So we've solved for a sub n. Fabulous. Checkpoint. Now that we have the missing leading coefficient, we put it all back together here. So we have f of x being equal to negative 3 times x plus 2 times x minus 2 times x plus I times x minus I. That is factored form. Unfortunately, I want standard form. So it's going to be a distribution fest. So much foiling, so little time. Drop down the negative 3. We're going to FOIL the real things together and FOIL the imaginary factors together. This becomes x squared minus 2x plus 2x minus 4. The second one, again, is difference of two squares. Square the first term, subtract square the second term. If you're thinking, Miss Quigley, the real things were also difference of two squares, you're correct. I'm just trying to show you a process that'll work when they're not. So we would double distribute, yes.
I already know what's the sign of I.
We will. So in this next step, we will go ahead and use our spidey senses. I squared is -1, so it means flip the sign. I'm also going to condense the middle terms here. This is x squared minus 4, and then x squared plus 1. Where'd these go? They canceled out, yeah. So these cancel out. Like I said, FOIL fest. Because guess what we have to do again? Yeah, we're going to FOIL again. This becomes x to the 4th power plus x squared minus 4x squared minus 4. I'm not drawing my like arrows because it'd be too much, but do we see invisible arrows in our head? X squared times x squared times 1, -4 times x squared, -4 times 1. These terms would condense down together because they're like terms. Whoa, what? This would be -3 times x to the 4th power minus 3x squared minus 4. And our distribution fest ends with a cute little distribution of -3. So our f of x function in standard form is -3x to the 4th power plus 9x squared plus 12. Oh my goodness.
That's the answer.
Yes. I asked for a polynomial function in standard form. Let's go back from top to bottom though, because now that we've like panic written everything, let's like actually go see what we did, right? So if we look from start to finish, is that too small? Okay. We started off by doing what? What did we do here? Roll all of our what? Factors, yes, and they're the opposite signs of the zeros that we were given. After this step, that's our setup step, we need to figure out what a sub n is. We use the like example they gave us for the x value and the output value. Here's my output. My x value would be the number inside those parentheses, so I plug it in and I just have to PEMDAS. This is 5. This is 1. This is the difference of two squares. Spidey senses, change the sign, multiply, divide. We find the leading coefficient. Put it back in, boom. So this and this are the same except that I put -3 right here. Well, bow. After this, we're just trying to get from fully factored form to standard form, and it's just distributions. If you don't see the pattern for difference of two squares ever, you just stick with foiling. That's your vibe. Sometimes you're going to have to be doing triple distribution on these kinds of problems. That's okay. Draw your arrows. Draw the arrows. We distributed. I squared is -1. Combine like terms. We distributed. Combine like terms. We distributed. Ta-da!
Is this gonna be on a quick
There is no more, so no, it will be on a test and on your homework. I highly recommend not leaving this homework assignment for far too long from now. This is a homework assignment that doesn't have a lot of questions on it, but it's going to take you a good amount of time. Take your time. Use the quad paper that I told you to get to organize and draw straight lines, because if you try to do it crooked on a page, you're going to get lost. Look how nice and neat I wrote this. That was on purpose. Follow the lines as you go on through your homework.